Benzene into benzoic acid, there's benzene, then there's benzoic acid. We're interested in stage 2, in which we take the methyl benzene, so there we are, and react it up with alkaline potassium manganate 7, otherwise known as potassium permanganate. And so there is the reaction we're doing, going from methyl benzene to benzoic acid. Now let's think about the rest of the equation, because it says it wants a balanced equation. So we can use O to represent the alkaline potassium permanganate, which is nice, but we also have to look at the rest of the equation. We got 3 hydrogens here that have turned into 1 hydrogen there, so therefore we're going to have 2 hydrogen atoms on this side. Now it's not going to be 2 hydrogen atoms, it's not even going to be H2, because what we got here is we've got all these oxygens floating around, so it'd be H2O. Now that means that we need 1, 2, 3 oxygen atoms, which I'm going to write like this. Some people would argue you don't need that, you should just use the O to represent it, but I do want to emphasize that every time you do this you are incorporating 3 oxygen atoms into the whole reaction. You can tell that it is an oxidation, because if we look at the oxidation numbers, hydrogen is plus 1, so 3 hydrogens plus 3, so the carbon must be minus 3 here, and then over here you got hydrogen plus 1, each oxygen minus 2, so to make that whole thing balance, the carbon must be plus 3. So the carbon goes from negative 3 to positive 3, oxidation number, it is oxidized. Why did you add hydrochloric acid at the end? Well, we talked about this in an earlier question, question 4, because when you use the basic or the alkaline potassium permanganate, then you don't make the acid, you make the conjugate base COO minus, which you then need to acidify to get to the acid COOH. And here we go. Methyl benzene, oxidized benzoic acid, heating strongly with an alkaline solution of reagent R, followed by treatment with solution S. Benzoic acid can then be used to produce all other kinds of compounds. Here's a little reaction sequence here. Well, what's reagent R that we use for the oxidation in alkaline solution? We've just seen that. It is MnO4 minus, the manganate 7 or permanganate. And then of course when we do it with the basic permanganate, that gives us the COO minus, which we need to acidify. So therefore dilute acid is S. Once we've made the acid, then we turn it from the benzoic acid to the phenyl methanol. And so this is a reduction. Okay, going from the acid through the alkali to a primary alcohol. In order to reduce an acid, we can't use the weaker NaBH4. We have to use the lithium aluminium hydride in ether. And then finally, and we're just doing this for fun, really, because this is not an oxidation that we're about to talk about, going from the phenyl methanol with HBr to compound U. That is just a substitution, substituting the OH by a Br. So butanol, converted liquid butanoic acid, one-step reaction, get the reagents and the conditions required, while primary alcohol going to acid is an oxidation. So we use our acidified chromium 6 or the acidified permanganate. Frequently produces a mixture containing unreacted butanol and the butanoic acid. How can you separate 2 liquids? Well, anytime you've got 2 liquids, you ask yourselves, can they be separated by distillation? And the answer is yes, because acids have higher boiling points because there's more hydrogen bonding available to the acids. So fractional distillation will allow us to separate the presumably lower boiling butanol from the higher boiling butanoic acid. To reaction compound A shown below, compound B is a straight chain hydrocarbon, so no rings, with the formula C4H8. Well, C4, of course, would normally have 10 hydrogens, as it's only got 8 hydrogens. That means there's a degree of unsaturation. It can't be a ring, so this has to be an alkene. Okay. Now, the 4 possible alkenes, and we'll throw them out here just for fun, that have C4H8 are these ones, either the 1-butene, the 2 isomers, E and Z of 2-butene, or of course the 2-methyl propene there. Now, what type of reaction is taking place when compound A is heated with concentrated sulfuric acid to form compound B? Anytime you heat with concentrated sulfuric acid, it's almost certainly a dehydration. So you're removing water from that. And you could also regard that as being an elimination of water. So now the displayed formula of two possible isomers of A, well, if we're taking A and we're removing water from it and we're getting one of these, then all we have to do is just draw the primary alcohols, or excuse me, the alcohols that would leave you with these when you remove the H2O from it. So for example, butane 1-ol, remove the OH and the H and we would get a double bond there. Butane 2-ol, remove the OH and an H, we could either have a double bond there for 1 butene or a double bond here for 2 butene, and then of course we could get the various isomers from that. Another possibility that would give us the 2-methyl propene would be the OH there and the H there. Remove that and you would end up quite nicely with the double bond right there, carbon 1, carbon 2, carbon 3, and there would be the 2-methyl. And then you could also get, by dehydration, the 2-methyl propene from this one. There's the 2-methyl there, there's the OH there, remove the OH, remove the H, you'd have the double bond there. Again, you would have a nice 1, 2, 3 double bond there, 2-methyl group there. However, despite me talking about it quite a bit, you couldn't get that one, because when we look further at this whole thing, and we haven't talked about compound C yet, but what we're doing is we are oxidizing A to compound C, and tertiary alcohols cannot be oxidized, or they can be under very strong conditions, but it just smashes everything up. You certainly don't get nice, cute, readily identifiable compounds from it. Staying on this, now we are talking about C. What color change is seen when A reacts with the acidified dichromate solution? Well, dichromate, of course, starts as orange, and then it goes to the chromium 3, which is green. What type of oxidative reaction is taking place? Well, we've kind of already talked about that. It's an oxidation. Anytime you see acidified dichromate, acidified chromate, you know it's going to be an oxidation, because this is a super duper oxidizing agent. Now, the displayed formula of compound C, well, this is going to depend upon what A was in the first place. Okay, primary alcohols will go to the acid when you do it with this. Secondary alcohols go to the ketone. So here were our 3 possible alcohols. We have a primary alcohol there, that would go to the acid, butanoic acid. We have a secondary alcohol here, that would go to butanone, and then we have a primary alcohol here, and that would become 2-methyl propanoic acid. Should point out that at the A level, they claim that if you do this reaction, but you kind of stop it halfway through, then you can also make the aldehyde, which would be butanal in this particular case, okay? Or of course the 2-methyl butanal equivalent of this. I'm going to put it there, but quite frankly, when you have these really strong oxidizing agents, you're just going to go to the acid. 3-hydroxybutanoic acid, well, it's solid, can act as a carboxylic acid. There's the acid, and as an alcohol, there's the alcohol. This acid can be oxidized to an oxo acid by using reagents A. This oxo acid can be reduced back to the hydroxy acid by sodium tetrahydroborate 3NABH4. So we're going here from a secondary alcohol to a ketone, so that's an oxidation. And we can use any of our standard reagents. There is, of course, that collection that we have seen before. No issues at all with that. The reduction of the oxo acid, there we are, gives the 3-hydroxy butanoic acid, which is present as a racemic mixture. Now, what's meant by a racemic mixture? Well, of course, a racemic mixture implies that you have a chiral or a stereogenic carbon. Let's have a look, and you can see right there, this carbon is, of course, stereogenic because you've got an H, you've got a methyl, you've got an OH, and you've got this CH2COOH. So racemic mixture means that you have both enantiomers present in an equal amounts, equimolar mixture of the 2 enantiomers. There is one of them, mirror plane. There's the other one. Even though it's not required on the A level, let's recognize which is which. Hydrogen going back, oxygen high priority, then this one that's got the CH2 going to a C as opposed to C going to 3 H's. So 1, 2, 3, we're going clockwise, so that makes this the R. And then this one here, we go 1, 2, 3, we're going anti-clockwise, so that is the S. State the effect of racemic mixture has in plain polar light? None. Because this isomer would turn it one direction, this isomer would turn it in the opposite direction equally, and so as you have both there, they cancel each other out. Cinnamaldehyde, which of course smells like cinnamon, is 3-phenyl-prop-2-enal. Let's see where that comes from. There's the phenol, there's the ene, and there's the al. So we start. Aldehyde dictates this is carbon 1, so carbon 2 is where the double bond starts, carbon 3 is where the phenyl group is. Pale yellow liquid that occurs in the oil obtained from the bark of cinnamon trees. An organic chemist suggested the following method for producing compound M here from cinnamaldehyde. This is a very big question that you will have seen in other worksheets. Looking at different parts. All we're interested in here is let's look at stage 3. We want to do an oxidation from an aldehyde to an acid. Okay, easy enough to do. Just about any oxidizing agent will work. So you can use your acidified chromium 6, or you could of course use the permanganate if you want. I'd go with the acidified chromium 6. Bethan attempted to reverse stage 3 by using a reducing agent. So here we want to reduce an acid to the alcohol. To the aldehyde. I'm leaping ahead of myself here, going from the acid to the aldehyde. What's a suitable reducing agent that can use? And also, is there going to be a different product that could have been in purity? Well, anytime you want to reduce an acid, you have to use the stronger one. The lithium aluminium hydride in anhydrous conditions, usually ether. And of course, anytime you start to reduce an acid, yes, you will make the aldehyde, but then you can also reduce the aldehyde to the primary alcohol, which will look like this. So just taking our aldehyde and turning the aldehyde group to a primary alcohol.